Okay, so first I would like to thank the organizers, especially Max, for the kind invitation. Yeah, and my talk will be about some sort of intersection between recent developments in non-self-dual gravitational instantons and some sort of Twistor framework beyond self-duality. So this is the outline. First, I will give the introduction to the problem that I want to study in the context of these recent developments. Then the second part of the talk will be somehow the main technical part, where I will need to introduce some tools from Keter geometry. And then finally, the main results of the talk will be given in the last part, together with some perhaps puzzles or questions that I've been thinking about. So yeah, so it will be a sort of very hand-wavy motivation, but roughly speaking, we can separate our understanding of gravitational phenomena, at least according to GR, into two different regimes. On the one hand, we have the large-scale structure and the behavior of the gravitational fields and how it's summarized by a number of major conjectures in GR. So there is the weak cosmic censorship conjecture, which was posed by Penrose, and tells you that the complete gravitational collapse of a massive body should result in a black hole. Then there is the final state conjecture, which tells you that more generically, the end result of all generic gravitational processes should be one or more black holes plus some gravitational radiation. And then there are some uniqueness results that suggest that if you have a stationary asymptotically flat vacuum black hole, then it must be Kerr. It must be the Kerr solution. So this, I would like to emphasize that this somehow highlights the relevance of Kerr, not only because it's an exact solution of given in closed form of the Einstein vacuum equations, but somehow in the big picture of GR, because this is fully non-linear and dynamic. So this is really what, in some sense, is physically interesting.
But the last one is actually a theorem, right?
Yeah, well, some people would say, well, if you assume real analyticity and so on.
Okay.
So on the other extreme, we have the microscopic structure. And this is, I guess, in some sense, the problem of quantum gravity is still mysterious. And as we all know, there are a number of approaches to this. But in particular, as a motivation for this talk, I would like to highlight the Euclidean approach to quantum gravity. I thought this might be kind of appropriate in the sense that this was proposed by Colin, and we are now in Cambridge. And in this approach, one is interested in something that is called gravitational instantons. These are solutions to the Einstein equations in Euclidean signature, which are complete and non-singular. So, and as I was saying, at the level of the large-scale structure, we have some sort of uniqueness for Kerr. Kerr plays a distinguished role. And by analogy, this was in Lorentz signature, by analogy in Euclidean signature, people conjecture the Euclidean black hole uniqueness conjecture. Proposed that the only asymptotically flat gravitational instanton is the Euclidean Kerr solution. And this, one might expect this to be true by analogy to the Lorentzian case, but it is actually not true, it is false. And the counterexample was found after many decades, only relatively recently, 10 years ago or something, by two authors, Chen and Teo. And I will describe what this counterexample is in the next slide. But let me emphasize again that this is quite a remarkable result because Kerr, everybody knows Kerr, and there is a good physical reason to expect that Kerr is unique at the level of the large-scale structure. But when you go to this microscopic structure or whatever, in the Euclidean regime at least, Kerr is not unique. There is something else, and that something else is the Chen-Teo geometry. And as as I said, this was found by Chen and Teo, two authors from Singapore. In 2011 and 2015, they had a new asymptotically flat instanton that is not in the Kerr family, but is really regular. The solution is non-self-dual, it's non-compact, it has this topology. It's got two parameters and two commuting Killing fields. So this is the toric condition. It was constructed with the Belinsky-Sakharov method with 3 turning points. This is also called the inverse scattering method. And more generally, Chen and Teo also managed to find the bigger class of solutions, which is also really remarkable. It's in general not regular, so it's not really an instanton, but it is still a Ricci flat geometry that is very, very interesting. I will call it the Chen-Teo family. It depends on 5 parameters. And they show that it contains not only the Chen-Teo instanton, which they previously found, but also is some sort of, as they say, some sort of interpolation between 2 extremes. The Ricci flat Blavatsky-Miansky spacetime on one extreme, and the Gibbons-Hawking with 3 centers on the other extreme. So, but well, Chen-Teo depends on a parameter that interpolates between the 2. Yeah. So this as I mentioned, this I believe is quite an impressive result. It's really interesting, but unfortunately, perhaps it took some time for people to start appreciating the importance of the relevance of this result. But luckily, in the last few years, there have been many exciting developments about this new instanton, and I would like to mention a few here. So, well, first, there is this very nice work from Gunduri and James here in the audience about the existence and uniqueness of toric asymptotically flat instantons. And as Chen was explaining to me earlier today, this is based on a formalism that is called the rod structure formalism. Then I will not really use the rod structure formalism here, but rather a result that originates in a paper by Stefan Acksteiner and Lars Andersson, who show that Chen-Teo is actually one-sided type D. What this means is that the Weyl tensor, if you look at the Weyl tensor, one side, the self-real part is type D, and the other part is algebraically general. This has a number of really interesting consequences, because it implies, for example, that the solution is Hermitian, so there is an integral complex structure. It is actually conformally Kähler, and it also implies that there are no Lorentzian sections. So this new solution really lives in Euclidean signature. It is not an analytic continuation of anything else. Then there is this very nice work from Paul Todd, which actually was a big inspiration for me to develop what I'm going to present here. And he showed that he gave a formulation of the Ricci flat one-sided type D matrix in terms of a single scalar equation, which is called the SU infinity total equation. This will play a crucial role throughout this talk. Then there is this remarkable result of Picard and Gauchon, who gave a classification of instantons. And because there is, of course, a natural question is, once you have found a new instanton that is different from Kerr, is there anything else? And what Picard and Gauchon showed is that under these assumptions of Hermitian, ALF, and toric, those are the only possibilities. Tau nat or tau volt, Kerr and Chen-Teo. Then there is another recent work by Ming Li, who apparently, if I understand correctly, removes the toric assumption in this theorem. Well, then Picard, Gauchon, and Lebron started some nice study concerning the modular space of instantons. And then there is this very nice work from Maciek and Todd and Paul this year about the Twistor theory of the Chen-Teo metric. And we heard last week's talk from Paul in the Twistor conference about this work. So, so before moving on to the second part of the talk, where I will introduce the main technical tools in some sense, let me try to describe some open problems in this field. So first of all, there is of course the role of the new instant in quantum gravity, in the sense of the path integral or the partition function. Then a very interesting problem that was emphasized a number of times to me by Lars Anderson is that what happens if you include more turning points in the Belinsky-Sakharov method. As I said, Chen-Teo was constructed with 3 turning points, but you know, the Belinsky-Sakharov method works for any number of turning points, and there could exist completely new undiscovered instantons with this method. This is a really fascinating open problem. I was also talking to James and Max about this. And then Einstein and Anderson formulated the question of whether there are non-Hermitian Ricci flat instantons. Because since they proved that Chen-Teo is Hermitian, it follows that all known examples are Hermitian. So this is an interesting question, and if they are, where is the complex structure coming from? This, of course, is related to a number of problems or questions in Riemannian geometry, such as uniqueness, existence, classification, the understanding of moduli space, and so on. And then finally, for this talk, all what I say so far concerns the Ricci flat case. But what about non-Ricci flat extensions of the Chen-Teo geometry? And these are relevant, for example, in physics in the context of supergravity, ADS-CFT, or some other theories, where you're interested in Einstein-Maxwell instantons, or you want to do the cosmological constant, or things like that. Also in the context of pure Riemannian geometry. And this is what I would like to address in this talk. In particular, Chen and Teo left as they say, as a challenging open problem, the construction of non-vacuum extensions of the metric. And this is in this talk I would like to somehow propose an approach to this problem. And the approach will be based on some sort of tools from Twistor theory that are related to Killing spinors, and to something that is called the S-infinity Toda system. So, well, first of all, what is a Killing spinor? Well, this somehow arises naturally in the context of Twistor theory, because you know, one possible approach to the construction of Twistor space, if you follow, for example, Penrose and Miller, is via the valence 1 Twistor equation. This, of course, has some strong, this imposes some strong restrictions in the curvature. So maybe a natural thing to look at is the next simplest case, which is the valence 2 Twistor equation. And the solutions to this equation are called Killing spinors. This is the valence 2 Twistor equation. So you may wonder, for example, in Twistor space, what is this object? And if you're in flat Twistor space, this is a holomorphic quadratic surface in Twistor. It was shown by Penrose. If you're in a conformalized dual space, then it's a little bit more complicated. This is some special holomorphic section of this thing, which is the canonical bundle of Twistor space. And this was shown by Corbin in 1982. I believe we heard we saw some instances of this construction in some of the talks last week, probably in Claude Lebrun's talk, and perhaps also in some Celestia talks. But the interesting thing is that the Killing spinor condition does not require the bicurvature to be self-resolved. So it is a bit more general. So in particular, if you have a vacuum type, Petrov type D space, such as Kerr, then you have a Killing spinor. This is usually referred to as the hidden symmetries of Kerr. And this was found by Walker and Penrose.
And related to this Carter concept.
Yeah, exactly. The Killing spinor gives you a Killing Young tensor and a Killing tensor, and eventually the Carter constant. So But in this talk, as I mentioned, we're interested in non-rigid flat geometries. And here there is but we want to impose the existence of a Killing spinor. So now the interesting thing is that there is this nice work from Magic and Paul in 2009. They established an equivalence between, so if a four-dimensional Riemannian manifold has a real Killing spinor, if and only if it is conformally Kähler. So this immediately connects the existence of Killing spinors with Kähler, conformally Kähler structures, without any conditions on the curvature. So this is really something that we will use in this talk. Well, okay, so as an example, let me mention, probably everybody is familiar with this here, but this is something called the Gibbons-Hawking ansatz. This is a class of four-dimensional Riemannian metrics, which depends on, well, there are two variables here in some sense, this scalar function B, and there is a one form A. And such that these equations are satisfied. There is some differential relation between the one form A and the derivatives of the scalar function B. So this has an integral condition. So this has an integral condition, which is the flat Laplace equation in 3 dimensions. The point is that this Gibbons-Hawking ansatz includes many interesting examples, such as well the tau-nat, Iguchi-Hanson, or more generally all the multi-instantons are particular instances of this construction. The thing is that this class of metrics is hyperkähler. So this means that there is a two-sphere of complex structures with respect to which the metric is scalar. In 4 dimensions, this is the same as these conditions in the curvature, that it is rigid flat and the right tensor is of the order. So the Gibbons-Hawking construction gives you, for any solution to the Laplace equation, a hyperkähler metric via these answers. This will actually play a very important role in this talk. And more generally, what you can show is that if you have a hyperkähler metric and you require the existence of a Killing spinor, then it must necessarily be given by the Gibbons-Hawking ansatz. And conversely, the Gibbons-Hawking, any Gibbons-Hawking metric has a Killing spinor, which is non-parallel. It's a non-scalar. So the metric is Kähler, moreover, is hyperkähler, but it is also conformally Kähler, with a non-constant conformal factor. This perhaps is not emphasized too much in the literature, but it follows from the existence of a Killing spinor. So this is a class of instantons that, of course, have been studied a lot, and they will play some role in this talk.
Bernardo,
yeah.
Would this? I mean, it can't be right as you say, because if you have hyperkähler, then any Kähler form already gives you a Killing spinor.
Right.
And it doesn't have to be Gibbons-Hawking.
No, but here I'm sorry, I should say non-parallel Killing spinor. Yeah, non-constant. Yeah, when I refer to Killing spinors in this talk, I will exclusively be thinking of non-parallel Killing spinors. That's hyperkähler.
You can't say anything more.
Well, I will say something about that in the next slide. Yeah, let me show you what I mean.
The Killing is going to be in parallelism independent from the Kähler form being parallel?
No, it isn't. Well, I mean, the Killing spinor is essentially the Kähler form.
And the Kähler form is
Yes, but so there are two geometries related by conformal transformation. So in one of them, so you have a Killing spinor. The thing is that the geometry, the hyperkähler geometry, has both parallel spinors and Killing spinors, which are not parallel. You can then reformulate things in terms of the Killing spinor condition. So, well, but these things have so in this talk, we're interested in geometries that satisfy three properties. They must have a Killing spinor, they must be non-Ricci flat, and non-self-dual. Those three properties. Now, the given Scottish ansatz has a Killing spinor, but is Ricci flat and self-dual. So we need a generalization of this. One possible generalization is this work from this remarkable work from Claude Lebrun about scalar flat Kähler geometry. And here, what Lebrun showed is that if you have any Kähler metric with zero scalar curvature and with the Killing field, then it must be given by this local metric. So we see here that this is a generalization of the Gibbons-Hawking ansatz. The novelty here is that, so you have a function W, which is, the same as the V in the previous slide. You have one form A, and there is another, the novelty here is this function, e to the U. So if you put U equal to 0, then this is the ordinary Gibbons-Hawking ansatz. But this is a bit more general. Now, what are the relations between these variables? And what Lebrun showed is that there is a generalization of the Gibbons-Hawking condition, which relates the derivatives of A, W, and U. And then this has an integrability condition, which is this equation in the middle here, which is called the monopole equation. Again, you can notice is that if you set U equal to 0, you recover the Gibbons-Hawking ansatz and the Laplace equation. But here this is a bit more complicated. And then there is finally another equation for the new unknown U. And that's this nonlinear PDE, and this is called the SU infinity polar equation. Well, as I say, this is a sort of generalized Gibbons-Hawking ansatz. I think the Lebrun actually says this explicitly. But the only thing is that this is a scalar flat Kähler. And this means that the Weyl tensor, you can show that it must be self-dual. So in terms of the three things that I was saying before, we need a geometry that has a Killing spinor, is non-Ricci flat, and non-self-dual. This thing satisfies two of these three conditions. It has a Killing spinor, it is non-Ricci flat, but is self-dual. So we will need a generalization of this. So in terms of of your question about if the Killing spinor is parallel, this is an example. Here, if you focus on the Kähler geometry, the Killing spinor is a parallel spinor. But when you go to any conformally related metric, that parallel spinor becomes a Killing spinor. Okay, so well, we need a generalization of this Lebrun's construction. And turns out that the generalization is very similar to the previous case. Namely, the metric is actually exactly the same. So now the condition, now we are asking a geometry that admits a Killing spinor. That's the only condition. Well, a Killing spinor and a Killing field. I will say more about this in a second. But then it turns out that you can show that the geometry, without any conditions in the curvature, so without any field equations, must be given by these ansatz. So it's the same, it's the Lebrun ansatz. The same values is exactly the same. The only thing is that the equations you get are a little bit more complicated, not too much, but so again, there is a differential relation between A, W, and U. Now it's a bit more ugly because if you remember the previous equation here, where here is just the derivative with respect to Z. Now in this more general case, you have something a bit more complicated. And then the corresponding monopole equation is also a bit more complicated. And the thing here is that there are no conditions on the function U. It is unrestricted. If you recall, in the previous case, I mentioned that U must satisfy the total equation. Here in this formulation, there are no conditions. So, well, let me first say what this Killing condition means, this Killing vector means, you can show that this has a Killing vector if and only if the Ricci tensor is invariant under the complex structure. So this is somehow a bit more. Well, so in the rest of the talk, sometimes I will say conformal killer with symmetry and sometimes conformal killer with this property. But because of this, they are the same thing.
So this is an assumption that this follows what you're writing down.
No, it is an assumption. Maybe I should clarify that. The assumption is conformal killer with this property. Sorry. Conformal killer with the J-invariant Ricci tensor. Those are the assumptions. It follows that then the geometry has a killing field.
This doesn't include the previous class.
Well, depends. No, yes, it does, because there are no conditions on U here. If you impose something on U, then you might recover this class.
Sure, you don't need both those equations for the integrability of J. J is your complex structure.
Right, and J, the integrability of J is included in these two equations.
Oh, just those.
Just
Not
regardless
the one
of
on
the,
U.
right. So that's a very interesting thing.
And J invariant just means summation.
Well, that it means that. So yeah, it's the analogous to the Hermitian condition. It means you have your Ricci tensor.
Yeah.
Yeah. Okay.
So is it understood that U is only a function of x, y, and z, or is it also allowed to be a function of V?
It's not a function of only x, y, and z. So this psi here is killing. Nothing depends on
Okay,
it.
so you want it to be clear.
Yeah, you want it to. You want yeah. Well, this is a. This comment will play an important role towards the end of the talk. The coordinate set here has a special meaning. The coordinate set is a Hamiltonian for the killing field. Because this killing field, the action is well, it preserves, it's holomorphic, it preserves the complex structure, and therefore it preserves the symmetric structure. So locally it has a Hamiltonian, and that Hamiltonian is this coordinate set. This will be important towards the end. And then, well, as I say, there are no conditions on U. So, so what we need to do next is to impose field equations, and this will give you conditions on U. So, and then we come to this remarkable work of Paul, that he gave a formulation like this for the case of Ricci flat or Einstein matrix, which was a big inspiration for me to develop this current one. And yeah, I've been talking to Paul quite a bit this during the program, and I have learned a lot. And here, what Paul showed is that for one-sided type D Ricci flat matrix, it follows that this condition, one-sided type D Ricci flat, implies that you have a killing spinor and a killing field. So all of what I said in the previous slide applies, but now you also impose a field equation, which is the Einstein condition. And Paul showed that this condition reduces to this PDE, which is the modified SU infinity Claude equation. And the function W must be given by this expression. So that's one thing that we will need. We are not, in this talk again, we are not interested in the Ricci flat case as an example in the Einstein case. So we will need this construction in the last part of the talk. Then we need, we are also interested in other field equations, as I mentioned, for example, the Einstein-Maxwell.
Is it like an Einstein version of the Bern-spectrum?
I don't know. It's a good question.
Or any other example solution?
Well, yeah, any one-sided type D, like Schwarz, you care, any of those.
Oh, these
Yeah. But which is only one-sided type D, Einstein. Well, I will say a little bit more about that.
Those
Yeah.
are non-self.
Non-self-view, yeah. But then there is something very interesting about that. I mean, let me later. So the other case we're interested in is the Kähler-Einstein, the Einstein-Maxwell condition. And here there is a remarkable connection between Kähler's geometry and Einstein-Maxwell metrics. This was found by Flaherty a long time ago in 1978. And this was found in the context of Twistor theory. As you can see from the title, this is the nonlinear graviton in interaction with the photon. And what Flaherty showed is that if you have a scalar flat Kähler metric, then it is automatically Einstein-Maxwell. You don't need to solve any field equations, they are automatically satisfied. The only thing you need to know is what the Maxwell field is, and what he showed is that the Maxwell field is the sum of the Kähler form and the Ricci form. So this is very nice, this is a connection between Kähler and Einstein-Maxwell. The only thing is that, as I mentioned at some point, scalar flat Kähler implies self-dual body. So that's one of the things that we don't want, so we need a generalization of this. There is a slide, there is a generalization by LeBron to the case of constant but non-zero scalar curvature, but this is also not the emotional thing we need. And the emotional thing we need comes now, and this was yet another connection between Kähler's geometry and Einstein-Maxwell. This, you can find this result in this work from Apostolov, Calderman, and Goldschon, and also from some work from Ledoux, which tells you that if you have a conformally Kähler metric with the J-invariant Ricci tensor, so with the Killing vector, then the cosmological Einstein-Maxwell equations are equivalent to only one equation, which is the Ricci scalar equals constant. So you don't need to solve the whole system of nonlinear coupled PDEs, which is the Einstein-Maxwell system with cosmological constant. You just need to focus on the Ricci scalar. If it is constant, then automatically it's a solution to the whole system. So that's quite remarkable to me. And now we will use this result in combination with the previous answers that I showed, because regardless of any field equations, I mentioned that there is an answer for the metric in terms of some variables, W, U, and so on. And using that answer, you can compute the Ricci scalar, and you can show that it is always given by this expression. There are no, without any field equations, this is just an expression, the calculation. So you see the sort of the total part of the total operator in some sense. And now you just, so combining these two previous results, you see that the cosmological Einstein-Maxwell equations are equivalent to this single scalar equation. So it's a nonlinear PDE, but in these variables at least it looks quite simple, quote unquote. And now before moving on to the last part of the talk, where I want to show you how this works in practice, let me give you a very simple example.
Sorry, your W in that last equation is still fixed in terms of the U as before, is it?
That's a very good question. No, but there is. I mean, W satisfies its own equation, or well, yeah, maybe I can say this. It satisfies that total equation and this equation. So these are the two equations. This is like the monopole equation. The analog is anything, but that's quite tricky. It turns out to be quite tricky in practice. I will come back to that.
That means that you really just have a fourth order equation on U. So you can take this at the bottom, solve it for W, forget about W, and plug it into the equation you were just solving. This shapes up to be fourth order.
Well, that's a nice thing to, yeah, I didn't realize. Yeah, okay. Yeah, so you get a single scalar equation for U, but it's fourth order. Yeah. I hadn't thought about that. It all depends on the answers you want to study. For example, if you start with a very simple example, which is this spherical answer, like 14 answers, but you leave f of R to be an arbitrary function. You want to solve your field equation. So what was the recipe to doing this? And well, according to what I've been describing, the first step is you choose an almost complex structure. There is no algorithmic way of doing this, of course, but somehow you can try to guess. Then you have to check that the geometry is conformally Keller and has a J-invariant rigid tensor with respect to the complex structure you have chosen. If this is true, then you know that you are in business in the sense that you know that it must have an SU infinity formulation. So you need to find the total variable. I'm not giving you the recipe for doing this here, but there is a well-defined procedure to find this. And then the last step is to solve the modified total equation, the SU infinity total equation. You can do this, which was this equation here in the end. So once you transform these answers into the total variables and plug everything into the total equation, you try to solve it, and you find exactly what you expect, which is the Euclidean Reisner-Nordstrom ADS solution. Just by solving one single equation, you recover what you expect.
Is Q necessary middle here?
Well, it's a constant of integration, the way it appears.
But it could be negative. Q squared could be negative.
That's right, yeah, you're right. Yeah, it could be negative. Well, now, yeah, we come to...
We just have told R equal constant and gotten the same solution.
If you solve R equals constant.
R equals lambda. Is that not enough equals we need to fix?
Yes, that's what I'm saying. But that's it. I mean, if you have any geometry and you solve R equals constant, how do you know that that is a solution to the field equations you are studying? Here, the key point is that R equals constant is equivalent to the whole system. Okay, so we come to the last part of the talk, and where I will try to apply this to the construction of non-backing Chen-Teo metrics. And well, we will see that there are some very interesting or unexpected phenomena. At least they are interesting to me. And well, so first, I apologize in advance because in this last part there will be many explicit formulas, but we do not need to understand in any detail the calculations. But I think I just want to show that everything is kind of nice in the abstract formulation, but when you want to solve something in practice, it can get very messy. And so to begin with, let me show you what the Chen-Teo geometry, rigid flat geometry is, the way that Chen and Teo found it. So you see that it's this terrible expression. There is well, this is 4-dimensional, so there are 4 coordinates. You have tau and phi are Killing fields, and then there are 2 coordinates on the other space, which are x1 and x2. And then there are a bunch of other functions here, capital F, H, G, capital X1 and X2. So it's really, and when you want to know what this is explicitly, but it's even worse. So this is what Chen and Teo found. So I also thought, well, perhaps I can show this explicitly to emphasize that it was not an easy example, counterexample to find, counterexample to Euclidean black hole uniqueness. It's not something that you can guess, or that I can guess at least. It's really a complicated geometry. And the way it's written here, it depends on 7 parameters. So there is a parameter k. There are 5 parameters in these polynomials, A0, A1, A2, A3, A4. And then, well, there are these complicated functions, and there is an extra interesting parameter which is called nu. This nu that appears all over the place. This nu is what I mentioned in the beginning, that the Chen-Teo interpolates between 2 extremes, rigid flat Plewansky-Miansky and 3 centers Stevens-Cohen. So those 2 extremes, nu equals 1 and -1, Chen and Teo show that this complicated thing reduces to those cases. But this is for any value of nu, this is a solution to the rigid flat equation. So what I want to do here is to construct a non-vacuum extension of this geometry, a solution to other field equations.
What signature is this?
Riemannian, it's positive definite. Yeah, you have to argue about the range of the coordinates so that this is Riemannian, but this function is negative, so that's why it is minus. But yeah, it's Riemannian.
So is it self-dual?
No, it's just rigid flat.
Rigid flat, okay.
Yes, that's the only thing.
And this is on CP2 minus.
That's right, yes, that's it. And well, so what I want to do here is to construct a non-vacuum extension to this geometry, and the approach will be to assume these ansatz, but leave the functions arbitrary. So we assume these ansatz, this equation star here, but as we did in the Schwarzschild case where we had a function f of r and we left it arbitrary, here we leave everything arbitrary. We assume this form of the metric, but we leave everything arbitrary and we want to solve the field equation. So yeah, let me show you how this works in practice. It gets quite messy, but there are some mysterious simplifications that I don't understand why they occur, but somehow it works. So this is the SU infinity formulation. Well, so yeah, again, I apologize for the explicit details, but what I'm trying to show here is that if you start from the Chen-Teo ansatz, from this ansatz, and you perform a coordinate transformation that I'm giving here explicitly, these kind of definitions, and you work out the details, then you can show that actually the Chen-Teo ansatz has a Lebrun normal form. It has exactly this form, where these, W, U, A, these are all defined in this expression. But this is the same, the Chen-Teo ansatz. There are no field equations, it's just the ansatz. Then you impose a conformal condition, well, you get some mess, some differential relations between the unknowns. And well, this is perhaps an important point for those of you who are maybe a little bit more familiar with the Chen-Teo metric. When you compute the Hamiltonian for the Killing field, as I mentioned, there is a special Killing field, which is this guy, d by the psi. When you compute the Hamiltonian, there is an integration constant, because the Hamiltonian is only defined up to integration, up to a constant shift. This integration constant, which I'm calling mu here, is exactly the parameter that interpolates between in the rigid flat case, between Lewansky-Miansky and Gibbons-Hoffman. But here there are no field equations, so we are already seeing that this parameter plays a special role without any field equations. It probably this has some interpretation in the context of symplectic geometry or dynamical systems or something. I don't know.
Can I just ask, so now you're in the scenario where this G, you're moving away from Chen-Teo, so the x1, x2, G and F are arbitrary.
Yeah.
But to put it in the Lebrun form and to make sense of a Hamiltonian, you need to define a Hermitian.
Well, that's this assumption here.
How do you, how do you pick a two form?
Yeah, of course, I'm not. So yeah, if we go back to this example, the first step, for example, this was to choose an almost complex structure. I'm not telling you how to do that, well, the way I did it is to somehow choose the complex structure of the rigid flat, or take some inspiration from the rigid flat case to define a complex structure, an almost complex structure, and then use that as an answer for the complex structure.
So you're saying you're taking what Steiner and Lars
Yeah,
worked out to be, and you declare this to be your.
Well, it's almost you can always do it. It's almost complex. I mean, it's equals to -1, and it preserves it's almost Hermitian. The thing is whether it is integral or not. But that's this condition.
But the equation is the one that relates W and A, the A being
Yeah, exactly. Yeah, and when you do that, you find these equations are exactly what you're saying. Anyway, you find this under these assumptions of the conformal Taylor geometry and the Killing field, you find this and this parameter that plays a special role.
Can I just check the Hamiltonian for dB psi?
Yeah.
Is that dB tau?
No, the Hamiltonian is d by d z. I mean, the Hamiltonian is z.
Sure, that's what the Hamiltonian is, but for which Killing vector is it Hamiltonian?
No, for d by d, yeah, this is tau essentially.
That's tau.
Yeah. Okay. So now, once you have done this, now you need to solve the equations. So you want to solve the total equation, which is this equation. Let's focus on the Einstein-Maxwell case with lambda equal to 0. And well, if you remember, there was an extra term here, u, y, but y, they call it y in this case is another Killing field, it's a second Killing field, but it doesn't appear here. So that's why this equation is a little bit simpler. But the point is that this equation looks simple in these coordinates. But you are given the Chen-Teo ansatz in those other coordinates, x1, x2, tau, phi, and so on. So this is what this comment here means. Xz e to the u as before means this. That's, yeah, we don't need to focus on the detail here, but there is some relation between the xz from Toda and the x1, x2 from Chen-Teo ansatz. You need to translate from one to the other in order to solve this equation. And this seems impossible because, again, the equation is very simple in this variable, but in the variables you need to solve for, it gets really complicated. So the thing is that there is a trick which I don't understand why it works, but somehow it works and it works in the sense that it allows you to solve the equation. And the trick is to do something really elementary, really simple. You just introduce an auxiliary variable, which I'm calling here a, via these two equations. So of course, if you replace in the total equation, this is 0. But this elementary thing allows you to, when you work out the details, at the end of the calculation, you arrive at this system. The thing is that now you can take cross derivatives in these two equations and subtract one from the other, and you end up with this simple equation, which is a dot here on the left, it means derivative with respect to d del x1, and on the right, it means derivative with respect to d del x2. So these are functions in different variables, so they must be polynomials. So from this elementary trick, you solve the total equation, and you find that the solution is really given by a fourth order polynomial. So there are 5 constants of integration, those are the parameters of the solution. And now that's it, you have solved the total equation. Now the puzzle is the following. As I mentioned at the beginning, at some point, the total equation is for if you want to solve the Ricci-Flat condition, then you solve the total equation and you determine everything. But here I'm solving actually the Einstein-Maxwell condition. It still boils down to the total equation. But now the puzzle is that you have determined x1 and x2, these two unknowns in the Chen-Teo ansatz, and by construction the geometry is Einstein-Maxwell. So again, you don't need to solve anything else. Well, in some sense, but by construction, equivalence to the equation implies that this is Einstein-Maxwell. But there are unknowns in the metric. There are still functions which have not been determined. These G and H are essentially the same as some of the total variables, W and A and so on. And the only constraint here is the monopole equation. It was this thing that comes from the top operation. But
didn't you have earlier equations for G and A, or the ratio, which told you about
yes, but that determines Xi once you know. I mean, the monopole equation is one extra derivative of this. It's an integrability condition for this. But doing that, by doing that, you get rid of Xi. So in the monopole equation, the only unknowns are the function h. Well, h is the only unknown. And then you still have to determine g. And Xi is given by this conformal Keller condition. Once you know h or w, you integrate this and you find Xi.
So can you remind us how is F
F,
related?
F is given by, that's the only thing that survives from the Chen-Teo. Yeah, the rest is completely arbitrary, but F is still given by this. There is some reason for that, but let me not. But well, that's let's see. So the puzzle is that any solution to the monopole equation will give you an Einstein-Maxwell-Chen-Teo method. So this is unlike any other black hole that you know, like for example, Schwarzschild has a Reisner-Nordstrom, Kerr has a Kerr-Newman, and you can go on for example, even Blavatsky-Miansky has a closed form, Einstein-Maxwell, Blavatsky-Miansky solution. But for Chen-Teo, what we are finding here is that there is a large class of Einstein-Maxwell-Chen-Teo geometry in the same sense that there is a large class of Gibbons-Hawking metrics. This equation, this monopole equation here plays a role analogous to the Laplace equation in the Gibbons-Hawking answer. So there are many solutions. For any solution, you know that the system is Einstein-Maxwell, but the metric is not given in closed form. So that is, perhaps that's just how it is. I don't know. I mean, implicitly, it is a solution by construction. The question is whether there is a way to single out the preferred solution. Well, and before
Sorry, what does the Maxwell field?
the Maxwell field is always the sum of the Taylor form and the Ricci form. That's the generic thing. And before finishing, let me then go through the cosmological case. And here we will encounter somehow the extreme opposite phenomenon. This is also, there will be another puzzle. Now you want to solve the modified Taylor equation, which is this terrible thing. It's really a terrible differential equation. And now, well, it seems even worse than before. But there's a generalization of the previous trick. Again, I don't understand why this works, but this does work. You introduce now two auxiliary variables, A and B, via this simple thing. You replace everything, and eventually this allows you to solve the system. So this elementary trick to solve this horrible equation. I don't know why, but it works. And, well, miraculously this works. And now you deduce that x1 and x2 are fifth order polynomials. In the other cases, we had fourth order, now with a power of 5. But the problem is that there is an extra constraint that involves the parameters in the answer. So let's see what this is. This will be an important point. So there is the parameter nu, which is related to the Hamiltonian of the Killing field. There is the cosmological constant lambda, and there is this parameter gamma. This gamma appears here, and this gamma, you can think of this essentially as the mass or the NAT parameter. Now, what are the solutions to that constraint? Well, the solutions are as follows. If you put lambda equal to 0, you get the standard Chen-Teo metric. That's Ricci flat, and that's you already knew. If you put nu equal 1, what you get after, well, long calculations is that this is the Blavatsky-Miansky spacetime with cosmological constant. You already knew that this existed. And then the other solutions are nu equals -1 or gamma equal to 0. In both cases, I should say nu equals -1 might be a little bit subtle. So yeah, there might be some subtlety here. But in either case, you get a self-dual Einstein metric, which is toric. By assumption, this was toric. The problem is that self-dual Einstein toric metrics were classified by Calderman and Peterson. So these are already known. So the problem is that there seems to be no ADS Chen-Teo from the point of view of this formulation. Because in the sense that you get solutions, but all of these were already known, unlike the Ricci flat case where Chen-Teo was not known. In this case, all of the solutions, because of this extra constraint, were previously known. And one puzzle for me is that if you look at the compact case, Lebrun actually classified all Einstein-Hermitian compact manifolds. Einstein-Hermitian in this context is the same as the assumptions I'm making, killing spinor and killing field and so on. But he also assumed compactness. And he proved that there are only three possibilities: the Fubini-Starling metric, or different blow-ups of the complex projective plane. One is the phase metric, and the other is something that is called the Chen-Lebrun-Weber metric. And this I checked with Claude last week. It is actually not explicitly known. They prove that the metric exists, but it's not known explicitly. And then the thing is that there are a number of reasons which I think one would expect a cosmological version of Chen-Teo to be a non-compact version of this metric. And if this existed, perhaps you could also, by taking some appropriate limit to the compact case, you could deduce what this is explicitly, which again is not controlled. So so let me then finish some conclusions and questions.
Around mu,
Yeah.
was it like strictly a constant, or could it have been functions of some of the coordinates that you probably derived it from some Hamiltonian relation? So you solved some PDE for it, and it wrote a function of it.
Right. In this formulation, it is actually constant because it comes from this. What you integrate is this equation.
Oh.
And this has an integration constant. So it's only, from this point of view, it's only a constant. But the meaning of mu is still mysterious to me. So, to finish, I have tried to argue that Chen-Teo is a remarkable counterexample to Euclidean black hole uniqueness in the Ricci flat case. We have seen that it's relevant for a number of research fields such as quantum gravity, Riemannian geometry, and so on. And what I have tried to argue in this talk is that by using killing spinors, which is the same as a conformal Kelly condition, which is the same as the SU infinity formulation, you can construct non-vacuum extensions of Chen-Teo. But then we encounter some new phenomena, which in the Einstein-Maxwell case, we find a large class of solutions, but there is functional freedom. The solution is not given in terms of a few parameters. There seems to be functional freedom. Now, one possible solution to this, which I don't know, but it might be that you, after imposing some instantaneous requirements such as regularity or some asymptotic structure, there might be a single solution in the same sense as in the Gibbons covariance you have the multi-instantons, but I don't know. And then for the cosmological case, what I try to show is that from the point of view of the S infinity formulation, the solution does not appear to be new, unless there is some subtlety in the calculations that could well be. So natural questions are, well, first of all, how restrictive is the Chen-Teo ansatz? And also, what is there any relation to the Chen-Lebrun-Weber metric, and can we construct explicitly this metric via this formulation? I don't know. I think this is reasonable to at least to speculate about. So yeah, that's what I wanted to say. Thank you.
So first, this functional freedom, I think it doesn't come as a surprise because in the scalar-flat-Taylor case, that's precisely what happens. That for any solution of the monopole, you get Einstein-Maxwell.
Yeah, that's right.
So that's just a comment. But so the way Chen-Teo constructed the metric is not like that, but by applying this beneath Zakharov. Now that's also applicable in the Einstein-Maxwell case.
Yeah.
So if you were to instead start with some fit solution,
Yeah.
I think what did they take? They took double Schwarzschilds.
Yeah.
So you might want to take double Schwarzschild Royston-Nordstrom
Yeah.
and repeat what they do.
Yeah.
Then you wouldn't expect this functional freedom, but you will zoom onto some finite parameter Einstein-Maxwell.
Yes, that could well be the case. And yeah, the thing is that that's a different approach using Galinsky-Sakharov or the Twistor construction that you pointed out from Woodhouse. But yeah, that could be a way out. And in any case, what I showed is that these are solutions. So the thing is, what is the Einstein-Maxwell Chen-Teo? Perhaps with that method, it's interesting because if you manage to find a solution, then this will give you the right solution to the monopole equation, which from this formulation you don't have any right solution, any correct, there are many. So perhaps by doing it that way, you could single out, you can understand more about this monopole equation.
Do you have a kind of geometrical formulation of this Chen-Teo ansatz?
Good question.
It looks a bit like orthotoric, but it's not. So.
Right. Well, we should talk about this later. But what I can say is that if you assume a Hermitian toric metric, only Hermitian toric and the Killing fields must be Hamiltonian, you can get quite close to the Chen-Teo form without assuming anything else. Not exactly the Chen-Teo answers, but quite close. But then you have to impose the Einstein condition in that answers, and then you might end up with the Chen-Teo form. Probably not. Probably there is something else because I would expect this idea of Chen-Teo to exist as a new solution. And from this formulation, you cannot get that. So there must be something else.
Klebansky and his collaborators, one of whom was Flaherty, I think, did a deep study of type D.
Yeah.
And on one side, and I'm wondering whether you try to apply their stuff to the modern approach. They had all kinds of recursion operators.
Well,
a very big theory.
Yes. I know some papers, but I think what I used that I think many of those things are there's this work from Paul Todd, or the one-sided Ricci-flat type D case, which is I believe Paul that was inspired a bit by some of Klebansky's collaborators.
There's another Polish guy that was in Mexico.
So from that point of view, that's what I have used, which I think it's very similar to what they did. But yeah, I know that maybe there are a few other things that I have not explored in that.
Any more questions? I was just wondering, so what kind of applications do people imagine for these Chen-Teo metrics? You said they don't have any Lorentzian
Right.
applications, so this will be used for something?
You mean physically? Because in Riemannian geometry they are interesting by themselves.
Or any application. Yeah.
Well, in Riemannian geometry there was this long-standing conjecture about whether curve is unique. That's one particular interest in this solution. And then that is relevant, of course, that is relevant for Euclidean quantum, right? Because then you have more space for the evaluation of involved.
So has someone computed the onto action of this?
Well, maybe Chen-Teo in the original paper. I haven't checked that, but that's maybe.
Okay, the science speaker.